So today we're going to talk about titration, and we're going to split this titration discussion into 3 separate videos. We want to talk today about how we would do calculations of a strong acid titrated with a strong base. And we'll cover other weak and strong combinations of acids and bases in the next couple of videos. But keep in mind that titration, and we've done titrations back in Chem 1, but it involves using a known concentration. Generally, we will use a base in many cases to neutralize an acid of unknown concentration. Again, it could be vice versa, in order to determine the concentration of that acid. The titrant is the solution that you know the concentration of. We put that titrant into a burette. We've used this before so that it can be easily measured. The analyte, or the titrand, is the solution that's going to be tested. This is the one we do not know the concentration of, and this is the one that we're going to determine the concentration of during the titration. The equivalence point or end point is the point at which just enough titrant has been added to another solution to cause it to completely react. An indicator is a substance that will show this end point or equivalence point with a change in color. They're usually weak acids. They have one color in their acidic form and another color in their basic form. And we generally use an indicator in the range of plus or minus 1 from the pKa. That's its useful range. So you're going to determine the pH at the equivalence point and choose an indicator with a pKa close to that value. So that's what we need. So a titration curve is a plot of pH versus the amount of titrant added. And these pH curves, or titration curves, excuse me, are going to be very characteristic for the type of titration that we're doing. If we're using a strong acid, strong base titration, then at the beginning, since we're measuring the pH of our titrand or our analyte, it's going to be, and if that's the acid, then it's going to be a very low pH when we start out down here. So we'll have a very low pH down here. And as it reacts, it's going to eventually, at the first, it's going to go through a period where it's in a buffer situation. The pH is not going to change very much at the beginning. But then all of a sudden, we're going to have this radical change right in here. And it's going to be a very steep, almost vertical rise in pH. And then it's going to level off then when we get done, since again, we're using a strong base, it's going to level up at a very high pH value here. So starts out low, has a very large distance here for that increase in pH. That's almost vertical. And it's going to have a central point at 7 if you're at 25 degrees Celsius, and then again end up high. So we'll look at some in future videos. We'll look at what the difference is in the titration curve when you're dealing with something that is weak along with something that is strong in the titration. So a typical problem. It says 100 milliliters of 1 molar HCl is titrated with 0.5 molar NaOH. Calculate the pH after 50 milliliters of the base have been added. Now, as it showed back here, the reaction for a strong acid, strong base is always going to be this. So you're going to have this hydrogen from the acid, the hydroxide from the base, you're going to have a completion reaction, and you're going to form water in the process. So that's always going to be the reaction for a strong acid, strong base. So that's what I'm going to write down first. We've got H plus OH minus, and it's going to yield water. Now, if it's strong, strong, the strong drives the reaction. There is nothing weak in this reaction because we're dealing with both HCl, which is a strong acid, and NaOH, which is a strong base. So that's all we need to do to know that we're not going to need rice at all because there's nothing weak in the system. It's all about CBAC. It's all about talking about the completion reaction, what the amount of each substance is before and after the reaction. And remember, this is the important thing. CBAC is in moles. CBAC because it's strong, and CBAC is always moles. So the first thing it gives us is molarity of each of those substances. So we're going to change those to moles first. So if I've got 0.100 liters of HCl and I've got a 1 molar solution, then I'm going to have 0.100 moles of my HCl. And if I've got 0.050 liters of my NaOH and I'm adding 50, or I'm adding a 0.5 molar solution, then I'm going to end up with a 0.025 mole value for my NaOH. So this is NaOH. Our solution over here is HCl. So this is going to be 0.100 moles of H plus, 0.025 moles of OH minus. And remember, we don't care about water at all because it's a pure liquid, so it's not even going to be involved in this. Another thing that we want to make sure that we know and we want to figure out at the beginning is how many total liters are we dealing with? Because remember, as soon as we get done with CBAC, the last part of CBAC, that last C is changed back to molarity. So we need to know that since we added 100 milliliters of our acid and 50 milliliters of our base, we've got 150 milliliters total of solution, which is 0.15 liters total. So that's another thing that we need to know. So now we have everything set up. And when this reacts, remember, we're going to find the substance that's going to be used up first, and that's going to be our OH minus in this case. So we're going to subtract off this amount from both. So we had our completion reaction, our concentration or amounts before, and when we subtract off those values, we'll get our amounts after. We've got 0.075 moles here, and of course we've got 0 for our OH minus. The last part of this for CBAC is to change back to molarity, which means we need to divide this by our total liters we found up there, which was 0.15 liters, and we end up with a value of 0.50 molar H plus. There is no other OH minus in here. This is a strong acid, so the pH is going to be determined from this value. The pH, remember, is the negative log of the hydrogen ion concentration, so the negative log of 0.50, which is going to give us a pH of 0.3, and it looks like we need 3 sig figs here, so 0.301 for our 3 sig figs for our pH. So there's our pH for this solution, very low pH. Now this is at the beginning, and through each one of these titration types, we're going to do a calculation before we reach the endpoint. We're going to do a calculation when the endpoint is reached, and then we're going to do a calculation for after the endpoint, so we can see what will happen at every point in this process. So in this next one, we've got the same system. We've got H plus OH minus yielding H2O. This time, we want to know the pH after 200 total milliliters of the base have been added. And we still have the same amount of hydrogen ion concentration that we had originally, which was 0.100 moles. Not concentration, amount of moles, remember, 0.100 moles. And now we need to know how much of our hydroxide we have. This time we've got 0.2 liters, and it's still 0.5 molar for our hydroxide ion concentration. So we're going to have 0.10 moles. Now, technically 100 because all of these were 3 sig figs. So 0.100 moles. And as you can see, what's going to happen here, since we have the same amount of both, we're going to subtract off the 0.100 moles from both, and what we end up with 0 hydrogen ion and 0 hydroxide ion. Now keep in mind that what this means is that we have no extra hydrogen ions or hydroxide ions. So what we have here essentially is a neutral solution. And a neutral solution pH is just at 25 degrees Celsius is going to be a pH of 7. So I'm going to put this in here, so hopefully this will jog your memory. You jot this down in your notes when you come back to it. So it's a neutral solution at 25 degrees Celsius. We'll have a pH of 7. Okay, so that's at the end point. That's at the equivalence point. So let's do a final calculation now. What would happen then after the end point when you go past that end point? So we still have, again, the same reaction. H plus OH minus, and it's going to yield H2O. We still have the same hydrogen ion or amount of hydrogen ions we started with, which was 0.100 moles. This time it says we're adding 300 total milliliters, so 0.300 liters times still 0.500 moles per liter, molar, and we end up with a 0.15 mole value for our hydroxide ion. So technically 0.150 moles of the hydroxide ion. So we're going to subtract now 0.100 moles of hydrogen ions, because that's what's going to disappear completely. And so 0.100 moles of the hydroxide will also go away. And we're left with 0.050 moles of our hydroxide ions. Now, keep in mind at this point, we have added our original 100 milliliters of our hydrogen ion solution, of our HCl solution, plus the 300 milliliters of our base. We've got a 400 milliliter or 0.4 liter total of solution. So we need to change this back to molarity. That's our last step always. So I'm going to divide that by the 0.400 liters of solution, and I get 0.125 molar hydroxide ions. The hydrogen ions were used up. That's not what it asked for. It asked for pH. Well, we know that pOH is the negative log of the hydroxide ion concentration. So the pOH is going to be 0.903. And we know that pH then is going to be 14 minus pOH. So 14 minus the 0.903, and we get 13.097 for our pH value for this solution.